Should get a little pop-up. Yep, there we go. Okay, great. Excellent. Thank you so much, Dylan. Okay, great. All right. It's 10 after 2. Sorry, it's 2 minutes after 10. So I think I will go ahead and get started, and I'm going to introduce our speaker today. I'm really delighted to be able to host and introduce this speaker. Dr. John Froehlich is a professor in computer science at the University of Washington and co-founder of Project Sidewalk. His research in human-computer interaction explores urban informatics, accessibility, and other high-value social domains. At UW, John is director of the Makeability Lab, associate director for the Center of Research and Education on Accessible Technology and Experience, and faculty chair of the Masters in HCI and Design program. His research has been recognized with 23 Best Paper and Honorable Mention Awards, a Sloan Fellowship, the UW Distinguished Dissertation Award, and multiple Google Faculty Research Awards. John was the general chair of Assets 2022, which is the premier academic conference in the design and evaluation of technology for people with disabilities. In 2021, he was selected for the UW College of Engineer Outstanding Faculty Award, and in 2022, the PacTrans Outstanding Researcher Award. John's also the author of an interactive textbook for physical computing, which has received over 500,000 views from more than 200 countries. The book introduces microcontrollers, sensors and actuators, basic signal processing and machine learning, and more through project-based learning. On a personal note, I can't recall how long I've known John, but I believe we met serving on the program committee for WIST, the User Interface Software and Technology Conference, probably more than a decade ago. So I can confidently say that in addition to all of those accolades that I just read out, John is also one of the nicest guys in the field of human-computer interaction. And so it is very much with pleasure that I am happy to have John here to talk to us all. Really relevant research to this project. So please join me in welcoming Dr. John Froehlich.
Thank you so much for that wonderful introduction. It really is an honor to be here, and I am humbled by your words. So as Celine already introduced me so kindly, I did want to recognize that everything I'm going to be speaking about is from my students, a wonderful set of students that span PhDs to masters to undergrad and even high school students. I also wanted to recognize we have a UW Create Center. I noticed there was a Create mailing list that folks were part of on when I was invited to give this talk. And this is a Center for Research and Education on Accessible Technology and Experiences at UW, and it was founded with a donation from Microsoft of over $2 million. I'm also part of PacTrans. So a lot of my work, and you'll see this, you might accuse me of not being a computer scientist. So it really intersects with urban planning and transportation engineering as well. So I do direct the Makeability Lab, and our mission is to design, build, and study interactive tools and techniques to address pressing societal challenges. And we really work across 4 kind of interconnected areas: environmental sustainability, health and wellness, accessibility, and STEM education. But today I'm going to be focusing on access, and specifically not necessarily digital access, but physical world access. So how can we leverage emerging trends in computer science and artificial intelligence to make the physical world more accessible for people with disabilities? And we work on a broad range of projects here, so I'll just start with 3. And the first is AR tennis. And the idea here is, can we leverage augmented reality and real-time computer vision to try to assist people who are low vision in playing sports, so broadening the participation of sports. And in a second, you're going to see somebody wearing a rather cumbersome AR display, but they're able to play tennis for the very first time in their lives. And my PhD student, Jay, did this, and he is an excellent, there he is, that's Jay, he's an excellent tennis player. So you can see that we're highlighting the ball here, and this is a massive design space. How best to highlight the ball, and perhaps you also want to highlight the trajectory or so on. But this is still early stage work, and we're really excited about it. A second project is augmented reality for sound. So this was work led by my PhD student, Dhruv Jain, who's now faculty at the University of Michigan. And the idea here is to, again, use real-time artificial intelligence, but to recognize sound, to improve sound awareness for people who are deaf or hard of hearing. So the watch is giving feedback about ambient sounds that are occurring, like the water running, door knocking. cat meowing. And in a brief second, for those dog lovers, dog barking as well. And then with my PhD student, Shazoo, we're working on indoor accessibility. And so in a second, you're going to see somebody scan their indoor space. And again, using real-time computer vision, we're trying to get and assess different aspects that could be inaccessible to people with disabilities. So this is using LiDAR and the RGB camera.
Please point camera at top and bottom of wall to initialize. Table. Detected throw rug. It's a tripping hazard. Table. Share.
So on the bottom, you can see a blueprint
Finish
that's being
button.
constructed in real time of that indoor
We detected
space.
3 issues in total.
But it's actually a fully interactive 3D reconstruction. And those red items are potential accessibility hazards or accessibility barriers for those indoor spaces. But I wanted to today talk about 2 specific projects. The first is Project Sidewalk, which Celine actually mentioned in the introduction. And the second is Street Reader AI, which I did during my sabbatical at Google last year. So for the first, our overarching question is how can we develop scalable solutions that assess and map the accessibility of urban infrastructure? And to motivate this work, I think most of you on the call are familiar with these things, but sidewalks are critical public infrastructure. At their best, they provide, an off-road pathway, interconnect us to mass transit, and provide just a safe route to schools and health services. But as we all know, city streets, sidewalks, and businesses are not accessible. In fact, here in the US, despite 88 legislation, our streets and sidewalks remain inaccessible. And this is a growing problem. So 20.2% of older adults, according to the 2024 US Census, have some serious mobility disability that affects their ability to walk or navigate stairways. So I want to pause here for a moment and ask, what do you see in this image? And I noticed that my slides are auto advancing, so I'm going to turn that off. Just give me one moment. Do not know why that happened, but let's just go back. Now I think I ruined the punchline here, but can you see the slides again? My apologies. Yeah, my slides were auto advancing, which was quite alarming. Okay, so
John,
yeah,
we're seeing your slide notes.
Oh,
again.
you see my slide notes. Okay. Thank you, Celine. Hopefully that will be the only technological difficulty we experienced so far. Okay.
Looks good now.
It was like a magician was advancing my slides. So yeah, so there's no curb ramps here, which provides street level access that allow us to cross the streets. And these are really a fundamental part of access in our cities. So for example, here I'm showing a video with somebody who's in a mobility scooter and they can't get up that curb ramp. And so they're left in the area of traffic. And so that presents a huge safety risk to people with disabilities. But also our cities can be inaccessible in other areas. So there is a curb ramp here, but there's also an impassable physical obstacle that makes that curb ramp inaccessible. Or sometimes our sidewalks will just stop, perhaps due to the jurisdiction of the city or it's the homeowner's property and they've only fixed part of their sidewalk. In other cases, you get surface degradation due to weathering or growth of trees and roots. Or in the worst case, you get a scene like this, which is fundamentally inaccessible to really all of us. You have physical obstacles, no curb ramp, and surface degradation. So an overarching question in our lab is how do these inaccessible sidewalks impact human mobility? And there's a lot of really rich research here in urban science and transportation, but we've also conducted our own interviews and workshops with over 150 stakeholders. And so I'm just going to show you a few videos of that and from other organizations to kind of contextualize the talk.
When I go to school in the mornings, I don't take the sidewalks, I actually take the street, and they shout at me from their cars. They're like, get off the road, and it's like, I can't actually use the sidewalk.
And here's another one, and this one is from Disability Rights Washington, where they attached cameras to people's wheelchairs and then also interviewed them about their experience with urban access in the city.
I rely heavily on sidewalks to be complete, to be maintained, but since that's rarely the case, it often forces me to go out into the street, which is not safe for me. I mean, definitely every trip I make, I'm out on the road for some reason or another due to the sidewalk conditions, whether there's no curb cut, whether there's, tree roots growing, so the uplift is just so steep.
So this lack of accessible sidewalks also impacts everyone. As you are maybe carrying luggage in a city, or you're pushing a stroller with your young child, or you're going on a bike route and you don't feel safe being on the streets with your kids. But the problem is not just the lack of accessible infrastructure, it's also a lack of data in the US. The National Council on Disability notes that there is no comprehensive information on the degree to which sidewalks are accessible in US cities. And my colleague, Professor Eisenberg, he and I have been working together about 5 years. He has studied this, and he found with 401 local governments, 13%, this is in the US, had ADA transition plans, but only 1.7% met minimum requirements. And there's also a complementary study done out of Oregon State where they looked at open data availability on government websites. And they found across a stratified sample of 178 US cities, 54% published things on streets, but only 20% on sidewalks. And even fewer cities had any information on access, for example, curb ramps. So the traditional way of getting this data is through on-site physical audits, walkability audits, which might be done by governments or local communities like Safe Walk to School. And these are great. This is the gold standard, but they're laborious, expensive, they're infrequent, and they're top-down. So as one example, in Seattle, we conducted our first ever sidewalk audit in 2017. It cost us nearly $400,000, and it's not been repeated. And it's interesting because it's really disproportionate to the value of that asset. So the sidewalks in Seattle are valued at actually $5.6 billion, right? So it's an incredible asset to the city and to the community. So in our work, we're pursuing a twofold solution. The first is how can we leverage online map imagery and computer methods to basically scalably analyze the built environment and sidewalks. And second, how can we leverage this unprecedented data to create new kinds of mobility tools and analytic tools? So I'm showing a little video behind me that has basically a view of Washington, D.C. with an interactive access score based on some sidewalk data that we've collected. And so our overarching vision is to map, assess, and visualize every sidewalk in the world. So this is something that I'm very excited about still, despite having worked on it for over a decade. So we have a large body of work that's examining various perspectives and avenues towards this vision. And this was started actually with one of my first Google Faculty Research Awards back in 2012, as well as with an NSF grant. And a lot of this work is about Project Sidewalk. So that's what I'm going to be focusing on for a large portion of my talk. So Project Sidewalk, if you ever get bored, even during this talk, you can go to projectsidewalk.org and you can try it out yourself. But it essentially combines online map imagery, remote crowdsourcing interfaces, and it utilizes that data to help train machine learning algorithms. In addition, the outcomes are around improving urban planning, creating new kinds of interactive visualization tools, and new kinds of urban analytics. And this could be for disability advocacy, this could be for walkability, and this could also just be for governments as they're trying to prioritize infrastructure investments. So how do you use Project Sidewalk? Well, it's kind of like a first-person video game, and we have two data collection missions. So the first is you find, label, and assess sidewalks. And the second is around quality control, validate and correcting labels. So this is the part of the talk that becomes interactive. So in Teams, you can actually, and this is actually a good way of seeing how many people are awake this morning. In Teams, you can use the little react buttons. And so I should be able to see, you're going to thumbs up and thumbs down different features. And actually, there's no thumbs down, it looks like in Teams. So instead, you're going to use the surprised face. Okay, so the surprised face if you disagree with something. Okay, so we'll get to that in just a second. But I want to introduce the exploring missions first, so that find, labeling, and assessing sidewalks. So like I said, it's kind of like a first-person video game. And here we're labeling these broken sidewalk panels. So we're dragging over the surface problem. And we just marked that as a problem. And then now we turn to the left and we're marking a whole bunch of no sidewalks, right? So we have this abruptly ending sidewalk here and we're dragging over the no sidewalk label and labeling. Is that the video coming through? Hopefully? Yeah, okay. So cool. So that's what it looks like. So at the top, we have 7 label types like missing curb ramps, obstacles and path, and so on. We have some mission stats, so we try to keep people motivated. And we have a mission map that guides you of where you're supposed to be labeling in a city, as well as that interactive streetscape imagery. So I want you to imagine that you're using the tool. And what do you see here? So is there a chat in this? Let me see. You can just chat. Although I don't know if I can find.
The chat
Actually,
button's at the top, so.
I see people raise, react, view, and more. But
Dylan just typed in the chat, so did
Thank you.
Emmanuel.
Yeah, I added in there to see if that helps it pop up. But yeah, it should just be right at the top.
it unfortunately doesn't for me. But well, that's fine. Hopefully Dylan saw that there is a basically a little uplift here. And I'll zoom in on it in a second so you can see. So this is a tripping hazard. You know, it's an access hazard. It's also a safety hazard. And you can see that either the city or the homeowner actually marked it in white. So it's been spray painted in some ways dealt with, mitigated a bit because the source of the problem, which was probably the tree that was pushing up that panel, has been removed. So you would click surface problem, and then you would click on the problem itself, and then you could rate the severity, add optional comments, and add some tags. So here's another example. This one is from our deployment in Mexico. And so hopefully you can see that there's a pole here and a pretty narrow sidewalk. There's lots of other access problems in this image. For example, there's no curb ramps at all, if you can see to the other end of the intersection. So again, you would rate severity and add comments. We mark 5 because this is not passable for somebody in a wheelchair. And we also marked the pole tag. So these tags are really important because while we have those 7 label types, we really want to know, and we know that that cities really want to know what the barrier itself is. So once you label something, you add in these tags, which gives us more information. And these are also important. So for example, in this case, you're going to see why poles are so problematic.
Up here with this pole, with these barriers, there's literally nowhere for me to go. I'm gonna have to get down the curb over here. Which I hate doing. And now I'm in the street with these cars turning. I know people have gotten struck by.
So to me, that takes my breath away. As soon as they're in a manual chair, they were able to navigate and get off of a curb, but now they're in the flow of traffic. So pretty dangerous for them. Okay, so that was labeling, but we also have these quality control features. And the one I'll focus on is this validation. So this is the interactive part where you can hopefully use the react button. So I want you to imagine yourself as a user. Is this an obstacle? So I'm using this yellow arrow to bring your attention to this pole and bike. So is that an obstacle? So you could do, yeah, so Celine's got it. So you could just react like this. Yeah, right. So you would mark agree in that case. How about this one? Is this a missing curb ramp? Pretty clearly, right? Also, there's stairs there. This is, again, in Mexico. So you would mark agree. Okay, how about this one? Yeah. Okay. Celine is really following along well. Dylan also got it right. So it turns out that driveways are utilized all the time by people to get down to the street if there are no curb ramps. But this is not a curb ramp. It's built for vehicles. And in the US, it's not ADA mandated. So there's no legislation about like tactile truncated domes, those warning strips, or other things. So while it's sometimes used for access, this is a driveway and not a curb ramp. How about this one? Is this an obstacle, this pole? Yeah, so in this case, it's also disagree because you have plenty of space to maneuver around, right? The city has to put their features somewhere, and in this case, there's plenty of maneuverability. And also this one is not on the pedestrian pathway, so this would be a disagree. So sidewalks, they often have these buffer zones. We really want people to focus on the pedestrian pathway. And in general, across all of our deployment sites, we've found that people are about 85% accurate in doing these sort of subjective judgments about barriers. So we also try to make Project Sidewalk fun and educational. We have badges, we have different kinds of mission structures, we have leaderboards, which have been particularly effective in our after-school programs. And I just want to emphasize, because it's a common confusion, you don't ever have to use your smartphone. All of the data is pre-collected imagery. And so in this case, I'm showing a person, a child who's labeling Mexico City from Germany. So you can do this from anywhere as long as you have a laptop and an internet connection. So I want to go through some of our deployments. Currently, we're in 42 cities, 10 countries, and 5 languages. Our partners have helped us translate Project Sidewalk natively into Chinese, into Spanish, and German, and other things. We've collected over 1.5 million labels and 1.3 validations. And it's crucial to emphasize that this couldn't be done without these community partnerships. So they're absolutely essential in bringing local knowledge to us and helping facilitate the deployments. And usually this is organic growth. So people will contact us. They'll say, hey, I've read about Project Sidewalk, or I heard about it. Can you come to our city? So in Amsterdam, for example, we work directly with the city as well as an international organization called worldenabled.org. We also worked with Burnaby. Okay, I threw this in there for you all, the Canadians. And so this is with Simon Fraser University. And it was part of the city's mobility access and partnership research partnership with Professor Atia Mahmood, who is in the gerontology department. And so this is a map of what they've collected. Nearly 1,000 users participated in this, collecting 20,000 labels. And these are, again, color-coded. So, for example, the purple is no sidewalk. Here are all of the problems. So this is obstacles, surface problems, missing curb ramps, and things like that. And as a quote, the city of Burnaby used Project Sidewalk to inform the implementation of new sidewalk programs and the expanded installation of bus stop programs. So essentially prioritizing where they want to put bus stops next to in sidewalks in their city. As another example, Newberg, Oregon. Here again, we work directly with disability advocates and the city. So the city actually put Project Sidewalk on their City Works webpage. And here we had 200 users, nearly 20,000 labels again. And you could see the purple, whereas no sidewalks are kind of around the periphery of the city. And you're seeing a greater density of problems in the downtown core. And so Project Sidewalk was used to successfully map the entire city and also establish new sidewalk renovation programs. In Chicago, Illinois, this is with my colleague, Professor Yochai Eisenberg. We're working with government, local schools, walkability advocates, and disability advocates, and we've collected nearly over 150,000 labels. I want to focus on one place specifically. Chicago is broken up into 50 different wards. So if we zoom in onto Ward 40, which is in the north part of the city, they have $1.5 million, this is last year, to decide what to do with that in terms of their infrastructure investment. And so the question here is, what is the equitable allocation and prioritization for pedestrian infrastructure improvements? And there's lots of different ways you could think about this. You could try to evenly distribute the money across a ward. You could invest money next to key facilities like hospitals or schools or libraries. You could instead decide to prioritize areas that have had limited investment in the past, and so on and so forth. And I don't think there's a right answer here. This is very, very difficult. But the idea is to use Project Sidewalk to help make data-informed decisions. And so they did their own analysis because all of our data is open. And here's some of the analysis they did. They had 3,000 curb ramps, 1,700 crosswalks, 1,000 surface problems, and so on. And what's interesting is, and I don't know if you have programs like this in your cities, but you can call in and report an issue with your sidewalk. It's oftentimes called 311 in the US. And so in blue, I'm showing sidewalk repair requests. And in red, I'm showing high severity problems found in Project Sidewalk. And while sometimes they correspond together, other times they don't. And so we are using this as an example to highlight that Project Sidewalk is more comprehensive. If you're just relying on your most vocal citizens to report sidewalk repair requests, you're not getting a comprehensive understanding of the sidewalk infrastructure in your communities. And so they used Project Sidewalk to help fund allocations. They ended up doing it where there were high severity problems in their ward. And fortunately, hopefully, we'll be using it in other parts of Chicago. As a quote again, Project Sidewalk helped us make better decisions in how to prioritize our infrastructure spending, as well as alert appropriate city departments to high priority accessibility issues. And I'll close these sort of case studies with Oradell, New Jersey. And it's really best spoken about by the Girl Scouts themselves. So I'm going to play about a 1.5-minute video of the Girl Scouts presenting this project to their city council, and hopefully the audio will come through.
We're going to have the Girl Scouts do their presentation on their accessibility report first.
Good evening, Mayor Didio and members of the council and distinguished guests. Thank you for the opportunity to speak to you this evening about Project Sidewalk and making our town more accessible.
Using a web-based program, we set out to label and map accessibility in Oradell. To facilitate the mapping, we divided Oradell into 5 sections. In total, we mapped 35.9 street miles across the town. In some cases, streets were mapped by multiple individuals. This helped increase accuracy.
81 volunteers from the Girl Scouts National MS Society and Oradell residents mapped the town. Altogether, we identified over 11,000 potential issues with an accuracy of greater than 93%. Some issues that we found are very minor, but some are very severe.
We then decided to take a look at which obstacles have the highest severity problems using data visualization maps. On the positive side, you'll see that Oradell has done a very good job of putting in high-quality curb ramps. Of the 733 curb ramps identified, only 13 were a high-severity problem. That's really great news. However, one of the biggest problems we see in Oradell is that there are a lot of missing curb ramps. And when they are missing, the problem is mostly severe.
Many of the high-severity surface problems arise because one part of the sidewalk has been pushed up by 1 inch or more, making it impossible or unsafe to travel across. This often is caused by tree roots pushing up the sidewalk.
Overall, our work shows that Oradell has invested significantly in curb ramps and crosswalks to ensure that the town is accessible.
To further improve the accessibility of the town, Oradell should focus on the high-severity barriers, preventing the disabled and others from safely walking on Oradell sidewalks.
Focusing first on curb ramps would be a quick win, but truly increasing accessibility also requires focusing on surface problems.
So to me, I'm just as excited about Project Sidewalk as a way of improving infrastructure and kind of advancing understanding of our cities as I am about using it as perhaps a service learning platform, where children get an opportunity to basically participate in data science with real world data and go through the full cycle of analysis, of visualization, and even advocacy potentially in their communities. So I think that could be very powerful. We have a case study paper on this in Oradell, and this really is being led by my colleague, Professor Eisenberg. And we've adapted multiple different parts of this curriculum so it can drop into US schools and fit within their curriculum. And we also have a version of it that would work in directly with the disabled community. We are also part of the SciStarter platform, so people can find out about this through their libraries or after-school programs and utilize it in a community science way. And I want to emphasize that all of the data that we're collecting is open source, and our tools are open source and open data as well. So for example, somebody found our data and built an interactive exploration of sidewalk accessibility data in DC, and this was covered by the local press. So we had nothing to do with this. Someone just utilized our data for that. Okay, but we're also utilizing our data in our own research. So Celine had reached out to me about this specific work. And really the key question here is, how do perceptions of sidewalk barriers vary as a function of mobility? So I've shown you lots of different images of barriers, but I haven't really focused that much on how they affect and impact humans. And this is a question that we explored as a function of 5 different mobility types or mobility aids. People who use manual wheelchairs, mobility scooters, motorized wheelchairs, canes, and walkers. And we built custom software to ask questions about different mobility features and barriers, and we had over 190 responses. So we curated the survey with 52 images from Project Sidewalk. We had obstacles like this pole. We had surface problems like this uplifted panel. We had curb ramps like this ramp, which is semi-passable, quite narrow and only really accessible in one direction. And we also had missing curb ramps. You'll notice that this intersection doesn't have curb ramps. So we had 3 different parts to our survey. For the first part, we had ratings, where we would show an image like this and ask, when using your mobility scooter or whatever mobility aid they said they used, do you feel confident in passing this? And you'll notice this is actually a missing curb ramp, but it's pretty low to the ground. So somebody in a manual chair might still be able to jump it, for example. So I'm going to show you a few different examples, and you'll see the respondents' choice on the bottom.
Sidewalk bearer images.
Oh, this should not have sound.
Seeing that.
Let's try that again. So in that, they said unsure. Here they're marking no. Here they're marking yes, maybe because there's another curb ramp available in that scene, and so on. In addition, we also did pairwise comparisons. So here we actually had them compare the, oh, I'm sorry, I don't have the right image for this, but we showed them two different images and had to compare which was more passable or accessible to you. And then for the ranking, we gave them different kinds of situations and actually had them rank the difficulty of passability for each of those things. We also showed them images to remind them of what these things actually looked like. So we found that there was a significant difference between mobility and usage and barrier passability. So for example, here I'm showing a low severity surface problem. So you see those cracks on the sidewalk. And I'm going to show you the responses. So we have cane users, walkers, scooters, manual wheelchairs, and motorized wheelchairs. And in green or teal, it's passable. In orange, it's impassable. And in yellow, it's unsure. So despite mobility aid, most people, a majority, found this type of barrier to be accessible. And that's what we expected because this was marked as low severity in the Project Sidewalk data set. For high, similarly, we found majority of people found these things to be impassable. So notice how the orange bars now are higher. But for medium, it was more mixed. The responses we found were motorized scooters and people in walkers oftentimes found these more significantly impassable than the other types of mobility aids. Here's a quote. "The cracks between sidewalk segments cause a constant uncomfortable bumping that also shakes my legs off the wheelchair's footplate. Roads are kept smooth, but sidewalks are not." And because I'm a human-computer interaction researcher, what I care a lot about is creating new types of tools. So we've been focusing on two. One is kind of an urban analytics tool called Access Score, and the other one is a personalized routing prototype. So towards the first, we're creating these, there's a little video here, interactive personalized scoring of the accessibility in your neighborhood based on the Project Sidewalk data and the result of our survey. So we can do these kind of weighted personalized scorings. So on the left, I'm showing walking cane where green is more accessible and red is less accessible. And on the right, I'm showing somebody who uses a mobility scooter, right? And so you'll notice there's less accessible neighborhoods for somebody who's using that type of mobility aid. We're also interested in doing these personalized routes. So yellow is the fastest. That's the route that Google Maps would give you if you said you were walking. Where green or sort of teal is somebody who's using a walking cane, and purple or blue at the bottom there is somebody who's using a motorized wheelchair. So all of this work in Project Sidewalk is the result of a fantastic group of students, faculty, and our community partners. We've had really over 100 people participate in these research projects over the years, and I'm really grateful for them. But I want to transition now to a second project, and then we'll take questions. So this part should probably take about 12 minutes, I think, 12 to 13 minutes. So last year, I had really the honor of being at Google as a visiting faculty researcher, and I kind of culminated lots of years of expertise and interests. So the question we kind of asked was, how can we make interactive streetscape tools like Apple Look Around, Meta Mapillary, or Google Street View accessible to all? And as I said, this is work I did at Google. So anything I say actually is not a representation of Google at all. It's my personal opinion. But this was with Alex Fiananca, who's in Google DeepMind, Nimr Jabber, and Victor Saran, who actually are both blind. And they were collaborators on this project, as well as Sean Kane. So I've been showing lots of different kinds of things with Google Street View. And here's Meta Mapillary and Apple Look Around. So these tools have really transformed how people learn about the world. You may have used them in your own lives to look at real estate, to kind of virtually travel to a new place. There's a lot of different uses of them, but they fundamentally rely on pixels. So Google Street View has over 220 billion images across 100+ countries. I mean, it's absolutely pervasive. but they're fundamentally inaccessible. So I'm going to play a video of someone using a screen reader with the current Google Street View.
Street View, application, image. You are currently on an image. To begin interacting with the contents of this image, press Control, Option, Shift, down arrow. No visible title to interact.
So despite all of this amazing information richness that's latent in these pixels, you get access to none of it as a screen reader user, right? So you can't really tell that you're in this street scene of New York and there's bollards along the sidewalk and there's these towering buildings and advertisements. So our question is, how can we make streetscape tools accessible to blind users? So let's try that same street scene again, but with our prototype called Street Reader AI.
AI description. The image shows a street scene in Times Square, New York City, with a wide avenue stretching into the distance, lined with tall buildings covered in bright billboards and advertisements. In front of you is a crosswalk with white stripes. You are in a sandy plaza facing the Treasury, a large ornate building carved into the sandstone cliff face. In front of you, 2 camels with colorful saddles. The scene is an outdoor view from a brick-paved walkway at Liberty State Park, with the Statue of Liberty visible in the distance across the waters.
And it's important to recognize that Street Reader AI is not just a context-aware image description tool. So those were all really image descriptions. It's really aimed at fundamentally being an accessible, immersive, and interactive Street View experience, just like you and I might be using Street View for. So let me show you another video. This one comes from our user study.
Where's the bus stop?
The bus stop is behind you. It's on the other side of the street.
Okay.
Great. Let me know if you have any other questions.
Now facing northwest. Now facing
southwest.
West. Now facing southwest. You can move forward 10 meters to 3950 East Stevens Way, Nebraska. Moved. You took a step 10 meters. Type a question to the AI and hit enter.
You typed, turn me towards the bus station.
Now
done.
You typed, what's ahead of me?
The bus stop is directly ahead of you. There are benches in a covered area.
You typed, are there any shelters in this stop?
Yes, the bus stop has a covered shelter with benches.
All covered. Beautiful. So no rain.
So in reflecting on this video, you could see that the user who is blind was fluidly interacting with that Street View experience, was engaging in this context-aware chat, and learning critical information that was otherwise latent in the images. So I want to reflect on how we designed Street Reader AI. So we worked with our 2 blind collaborators. We constantly were prototyping and revising and iterating on the prompts and the software. And we also got feedback from the augmented reality and geo teams at Google. And then we ran a user study with 11 blind participants. But even early on, we knew we were onto something. One blind participant said, I think there's massive value here. And another, this is just so exciting having a conversation about the street. This is really amazing. So we identified 4 core user tasks like place investigations, route planning, open-ended exploring, and virtual tourism. In terms of a system overview, the user interface was designed to look a lot like Google Street View, but there's also AI-specific components like AI Describer and AI Chat, as well as these screen reader status messages. So let's take a look at AI Describer. The key is that it combines both the GIS data, so structured information about the world, as well as AI analysis of the scene.
Generated description. The image shows a view from Alamo Square in San Francisco, with the user facing northeast. In front of the user, across a street with crosswalks, is a row of Victorian houses, known as the Painted Ladies. To the right, about 35 meters away, is the Painted Ladies Observatory.
So in order for it to have said to the right is the Painted Ladies Observatory and the 35 meters away, it needed to understand GIS information. So it's not just relying on the image itself. So the way this works, and you can trigger it at any time with Alt-D, we have a static prompt with prompt instructions to Gemini. We have an optional user profile. Someone can talk about whether or not they have a guide dog or if they use a cane or so on. We have dynamic input. So this is dynamic geographic context, the GIS structured data, as well as the image. And this is all fed as structured JSON into the multimodal LLM. And then we get structured data out of it. So we just diving into a little bit of this, the static prompt says you are an expert in describing visual scenes for people who are blind or have low vision. You will be assisting users who are navigating Google. And the prompt is actually quite long, and I'm not going to show it all here. And then, as I said, the optional user profile. For dynamic input, we include the user's location, like their lat long, their heading, road address, city, state, and country, some view metadata, nearby places, and their current view. And then for the output, we get structured output about mobility-related features, obstacles, and then that context-aware description that you heard. For AI chat,
how would I get to the houses from here?
To reach them, you would need to cross Steiner Street. There appears to be a crosswalk directly in front of you at the intersection of Hayes and Steiner.
Are there pedestrian signals or a stop sign?
I can see a stop sign on the far corner of the intersection to your left.
Can you turn me towards the park?
You are now facing southwest towards Alamo Square Park.
What do you see?
You are facing a large grassy park with a paved pathway winding through it, likely Alamo Square Park. There are several people visible in the park, and a building is partially visible to your far left.
So you can interactively chat with an AI backend, but also use it to command the software. Did you notice how I said, can you turn me towards the park? Right? So you're actually interactively controlling the Street View experience itself. So this is a far more complicated structure. I'm not going to go into details here, but we use Gemini Live for that responsiveness. So we're forwarding a lot more information as well as user history of their different interactions directly into Gemini. And then, as I said, we also have these command definitions, so the AI can actually control the software itself. In terms of our user study, we recruited 11 blind participants, and we had 3 tasks, these place investigations, open-ended exploration, and virtual tourism. And we started with a tutorial. I think this experience itself really demonstrates how important it is to make Street View accessible.
Your body.
Oh, that's okay.
So if you want, if you just want to turn, so to hit right.
Now facing northeast.
I'm facing east.
Now
And it'll
facing
tell you, watch.
east. You can move forward 7 meters to 235 Thompson Street.
So you can just navigate, you can move down Thompson Street as if you were actually in New York on Thompson Street.
That's so incredible. Wow.
So one of the things we didn't even expect is when we recruited our participants, none had previously used Street View. And that meant that they didn't have an understanding of what that was and why there would even be this immersive imagery out there. So that tutorial experience was really phenomenal for us because we got to see people's first experience of like, wow, you can go to New York from Seattle and travel around the city? You had access to that? So it's a really powerful, it's maybe something that you and I take for granted, but it is a really powerful experience. So I wanted to go through at least one sample task here from the first part of the study. And in this case, it's you plan to take your 2 young nieces to an unfamiliar playground. Your goal is to learn about the playground before going. So this is a pre-plan stage of travel, and you want to learn about that playground in order to inform your visit. So observe the diversity and type of questions asked in the system's responses.
Generating AI description. AI description. You are standing on a sidewalk facing a grassy park with a playground. A concrete pathway leads from the sidewalk towards the playground, which features swings and a play structure with slides. There are houses visible in the distance behind the trees.
How high is the slide in the park?
Based on the image, the slide in the park appears to be about 8 to 10 feet high.
What other play equipment is in the park?
In addition to the slide, there appears to be a swing set and some other climbing structures. There is also a paved walkway leading to the play area.
Do the toys in the park seem appropriate for toddlers?
Based on the image, the play equipment in the park seems appropriate for older children, not toddlers.
And then we also had this open-ended exploration. So people were to explore to a local ice cream shop, as well as explore a route to a Japanese restaurant. So I'll give you an example of this. You plan to meet a friend in Paris at a Japanese restaurant. Virtually investigate the walk from the nearest bus stop to the restaurant. You will need to walk north. Oh, that for some reason it says you cannot play the media. I apologize. But this was intended to be far more complicated of a task because they needed to move around whereas in the POI investigations, they didn't necessarily need to do that. So towards the user study results, overall, people really enjoyed using the system. They rated it 6.4 out of 7, and they predicted that they would use it in the future. Most navigation systems can get you to the last 5 to 10 feet, but this helps get you to the door and even describes it. This is just so exciting. Like I shared this one previously, having a conversation about the street. This is really amazing. We also identified key problems like spatial orientation, managing the truthfulness of the system, overall system limitations, and conflicting info. So sometimes the GIS data, which can be more up to date, would provide information about a business that wasn't actually visible in the image. And that would create contradictions. In terms of AI system uses, we didn't expect this, but people predominantly use the AI chat system, which I think is because it's inherently personalized. You're asking questions to AI chat that you care about versus AI describer is prescribing information that you might care about. So 87% of all AI interactions were chat. So this quote says, the more you ask, the more you learn. So our study really is the first to study how do blind people use Street View systems and what questions do they ask. And I know I'm low on time here, Celine, but just very quickly, the number one question was spatial orientation. Where am I? What am I looking at? Is the bench to the left or to the right of the shelter or within the shelter? That kind of thing. Object existence, and so on. I'm going to skip through this because we're just like a little low on time. Okay, probably you're thinking about this. If you're reliant so much on artificial intelligence, how accurate is the model? Well, we analyzed the question responses and the accuracy of the system, and we found that over 86% was accurate. And this is without any custom training or fine tuning of Gemini. This is just using Gemini Flash 2.0. We also found that 6% could not be answered. Like, for example, what buses use this bus stop? We didn't actually tap in. We didn't use RAG for it to actually query a system, so it didn't have information about that, or what food is served at this restaurant, and so on. And then for incorrect, our common errors were misidentifications, false negatives, and out of view problems. So I'm just going to kind of close here on some of the incorrect and mistakes, because they're also interested. So here, the system's going to make a mistake. Oh, hopefully it can play this. Oh, no, it can't. Okay. Well, they ask, I don't know, my system's having a problem. They ask about whether or not there is a pedestrian signal in this image, and the system says yes, but there's clearly not. And actually, they ask then a follow-up question. Okay, if there's a pedestrian signal, is there an APS? That's an assistive pedestrian signal. So something that would be tactile, a tactile response on the button. And the system says yes, and of course, there's not. But in some cases, the system behaved inconsistently. This is something I also brought up. So you notice that there's an old bike rack here on the bottom left. Let's see if I actually can play this video. Oh, I can't play this one either. I don't know what's happening. But some cases, the system would say, yes, there's a bike rack there. You can park your bike if your friend is going to join you at this restaurant. In other cases, it said no. So there was mistakes. So this is an example of where it got it right. I'm hoping I can play some of these videos. And then sometimes the users would ask questions before they actually got to a location and not realizing it, and the system didn't tell them. So in this case, they asked about whether or not there were tables and chairs in front of Ben & Jerry's, and there clearly are. Oh, it says you cannot play the media. So this participant thinks they're in front of Ben & Jerry's. Ben & Jerry's is directly to their left. The system isn't smart enough to move the view and to query the entire immersive imagery to understand what to look at. So it assumes that the user is looking at the correct thing and makes an incorrect response. And I'm sorry for these technical difficulties. So this is part of our larger vision, though, of creating AI agents that have more autonomy, that can go out and search online imagery and then properly respond to these questions. Right. So I think there's a lot of potential of doing that and building kind of a smarter solutions. In terms of other future work, combining multimodal data sources like real-time bus information, explaining data provenance. How are we getting the answer? Is it coming from structured GIS data or the images? And I'm really hoping we can. Oh, I can't play this one either. But this quote from this gentleman emphasizes that a tool like StreetReader AI is something that gives him the freedom to get lost, empowers him to explore the world in a sort of safe way from a cafe or from his couch and learn about the world before traveling. And he found that really, really empowering. And sorry that I wasn't able to play that video, but it's truly, I think, resonates because it helps capture what we were trying to do with StreetReader AI. So that's my last slide. I think we have about 9 minutes for questions. So hopefully you have some. Yeah, thank you very much for your attention.
Oh, thank you so much, John. That was just really, really, truly inspiring. And so much, like it's amazing the breadth of work and the impact as well, and the number of people that you've been able to get involved. And I love the fact that so much of that is sort of organic. So I think we should open it for questions. So if anybody wants to ask a question, please feel free to unmute yourself, turn on your video and camera and ask a question, or if you'd like to, you can raise your hand or type a question in the chat. John, I don't know if you could see the chat now. There actually is a comment in the chat from somebody about how impactful this is.
I love chat. I see people raise, react, view, And that's all I see. I don't see chat.
Oh, that's weird because chat is to the left of the people icon in
Yeah,
my.
there's nothing there for me.
Oh, maybe, I don't know. That's interesting. Maybe it's because you're a guest, which would be really sad and unfortunate. So I'll read
Yeah,
you the comment that is in chat. There's a comment from Gabrielle who says, "This looks like such an impactful project. My mom worked for many years with visually impaired and disabled students, and orientation mobility was a big part of her work and the challenges they faced. She's interested in sharing this with her former colleagues." So
Nice. Yeah, I mean, orientation and mobility, for those who don't know, is like a structured way of if someone's losing their vision or has lost their vision, it's a way of working with a professional O&M instructor of how to navigate the world, how to use your mobility aid. And yeah, that's definitely something that with my UW hat on, I think would be a great use case of something like Street Reader AI, so that people again can have that freedom to get lost in more of a safe place versus being out in situ in traffic and in other kind of risk prone areas. So thank you for that comment. And I'm sorry I can't see your chat.
that's okay. Paula, you have a question?
Hi, yeah, thanks. Thank you for this presentation. I really especially love the community engagement, the youth engagement part.
Yeah.
Makes me think about how we can do that in my own research. But the question I have, because we're thinking about engaging AI technologies in a platform that we're building, and I'm wondering about how severe the mistakes are for your platform. I know you pointed to a few of them, but how regular are those, and how do you go about sort of minimizing those
Yeah.
AI mistakes? Yeah.
Yeah. Are you talking about Project Sidewalk, or are you talking
Yeah.
about Street Reader AI? Yeah. So that's such a great question, and it's certainly something that is critically on our minds at all times. So I think there's a couple of different ways to look at it. The first is that the imagery we're using is from streetscape providers. So that could be from Google, that could be from Meta Mapillary. We actually work with some proprietary data providers as well in our European deployments. But that imagery is not the now, right, Paula? So that imagery may have been collected last year or 6 months ago. So there is a temporal gap. Now, remember in one of my early slides, I talked about the Seattle sidewalk audit and how they did that in 2017. Well, guess what? They haven't repeated it. So even that 6-month gap or a year gap or a 2-year gap, I would suggest is not that big of a problem. But the second key piece is, well, how accurate are people's perceptions, especially if you're relying on Girl Scouts who maybe don't have disabilities to label city streets and sidewalks. And I think that's a really, really important question. And we have a lot of different kinds of infrastructure to try to deal with that. I'm going to share my screen again really quickly. Gosh, I know I've had so many technical difficulties. Do I really want to share my screen? I'm going to try. Can you see it or no?
Yeah, we see it.
Okay. So so let's see. So let's actually go to Oradell, for example. So let's go to one of our tools called Gallery. I'm gonna blow this up so you can see it a little bit better. Does that work? Okay. So notice how you can mouse over really anything, and you can see what people have previously labeled. So for example, they've labeled this as a crosswalk. And notice how this has agree. Notice also that the community themselves, this has 8 positive votes, including 1 AI vote. So we also have AI in the background, which I didn't really have time to talk about, that is trying to monitor people's work as well and make assessments about accuracy. So this, and here's another one. This one's marked crosswalk with 5 positive votes. Here's a maybe more controversial one. And actually this one is a problem because this one is incorrect. Notice how it has 2 positive votes for agree and 1 negative vote. So I can make this bigger even. This is it. This is not a pedestrian signal. This is a street sign. So I got to disagree with this one. And now actually it'll enter into our data set where we have, when we publish this data, or if cities suck it down, they can see what these agreement rates are like. And they could, for example, just prioritize things that have, a disproportionate amount of agrees versus disagrees. We also have multiple raters come in and rate different things. So you could send 3 people down the same city street and then aggregate their data in some way. Okay, that was really long-winded. I apologize, and hopefully that was still interesting.
Just very quickly, in terms of the second project, the AI mistakes in sort of reading the affordances of the space, like what was available in the playground, how severe is that?
So we found this was 86% accurate. That was just based on our Q&A data set from our user study with 11 blind people. So I would say, as a caveat, that's a pretty small data set still. But guess what? We used Gemini's last model, 2.0, and they just published Gemini 3 this week. And it is doing so much better on spatial reasoning tasks. So I would suspect that if we reran the study, it would already do better. But what we need is better benchmarks. There's no good, it's called visual question and answering data sets for this type of data. And so that's really what we need so that when new models come out from OpenAI or Gemini or others, we have a good understanding of how things are progressing.
Right. That's really helpful. Thanks so much, John.
Yeah, thanks for your questions, Paul, and for your attention.
All right, I want to read you another question that's in the chat that you can't see. Somebody said, thank you for the impressive presentation. How do we evaluate the difficulty when obstacles are combined? For instance, a wheelchair user might feel confident tackling a single curb ramp, but if they had to navigate several such obstacles in, for example, 10 minutes, does that significantly increase the challenge?
Yeah, I think that's a great point. So we have a line of work, what we call access score, which is a lot like walk score, if you know about that, which is essentially a set of rules or algorithms for weighting different properties of the world and for walkability. We're trying to make that for people with disabilities. So I briefly mentioned Chu Lee's project where I showed the personalized routing map. I think it's a very difficult problem because ultimately it's hyper-personalized based on that person's own mobility and mobility judgments. But I would offer that if a route has multiple access barriers, it should be de-weighted more than a route that only has a single access barrier. But it, of course, depends on the type of barrier and the type of mobility aid that the person is using. And all of the vision we have is that all of that data should be available and should be infused in current mobility tools like Google Maps, right? And then you can tell it what your mobility profile is like, and you can actually see the problems. So you could make a judgment because all of this is image-based. Right. So then yeah, go ahead.
I would imagine that it's also contextually temporal and based on the destination. Like if you were thinking about going to, meet a friend for coffee versus going to an important doctor's appointment, the number of access barriers you're willing to overcome may change in the moment, kind of thing.
Yep, I totally agree. I mean, I'm a parent, so like I think about this all the time. It's like that is a huge context switch. If I'm biking alone and commuting by myself versus say biking with my children, I'm making vastly different choices about route, right?
Yeah.
That's just one example. Yeah.
Yeah. Great. All right. Is there any other last question? We've got 1 minute left.
Hey, I'll maybe jump in here quick. Thanks for the amazing talk and going through some of these, massive problems with some really, really cool ways of tackling them. I guess my question's maybe broad in the sense of, like right now you're doing a lot of stuff in the AR space and with the images, but where do you see this kind of the next step of this? Like, I think the obvious place my mind goes to is like AR glasses and things like that, but how much of a big jump is that transition to get into more, live level as someone's walking through their environment?
Yeah, I mean, that's the dream, isn't it? And of course, I have some students who are really focused on augmented reality. I think that most of the stuff I presented to you today was like pre-travel planning versus in situ, right? And I just think the in situ stuff is probably more like 5 to 10 years away, maybe even further, to be honest, although it's hard to make those judgments. It's just like, and it's going to be based on people's risk, their own kind of risk assessments. It requires so much data. When you have a live stream, you can get error cascading, so the context can get messed up and it just can be problematic. But that said, there are groups working on this. So Be My Eyes has a relationship with OpenAI. They're really great if you've not heard of them before, and they work with the Meta glasses. And then Google also has Project Astra, which is live feed analysis as well. From live video feeds streaming from AR glasses. So there's a lot of great people working in this space. I just think it's a much harder, and of course requires expensive hardware, a very fast, high bandwidth internet connection, and truly, a sacrifice of privacy. And so that's, a big big potential compromise and risk for people.
Yeah, I think it's a great point. And I think like obviously you're on both sides of it with the first example that you showed in the tennis, which is obviously a very simplified and safe version. I think that's where my mind goes to is, you know, not like only all of the complexities of it, but then now you're actually someone's live out there making decisions to potentially cross the road. And like I love where that's going, but I can see where you're getting at that we're still a ways away. So yeah, thanks for that insight.
Yeah, thanks. Great question.
Well, I think we are at time, and we want to respect everybody's time. So can everybody please join me in thanking John for this fantastic talk again?
Thank you. Really pleasure to be here. So thanks so much. Sorry for the tech difficulties, folks.
Well, and sorry that you didn't have access to the chat. I just don't know.
I know I sent you a screenshot. You know, I don't know. I'm not, like I said, I'm not a Teams user. The other thing, I don't know why my videos didn't play at the end there, but my computer was just giving up. But yeah, enjoy your Friday. Happy weekend, everybody. Thank you so much for having me.
John. Thank you.
Thanks.
Thanks so much.
Bye, everybody.
Yeah,
Thanks,
bye-bye.
thanks everyone for being here.
Thanks. Yeah.